Hey there, science fans. Have you ever wondered why things fall down? Like, why doesn't your lunchbox float away when you drop it? The answer is gravity. Gravity is like Earth's invisible hug, pulling everything towards its center. It's a force of attraction between any two objects with mass. The Earth has a lot of mass, so its gravity is pretty strong. That's why we stick to the ground instead of floating off into space. Gravity is super important in our daily lives. It keeps our feet on the ground, helps us pour drinks, and even keeps the Earth orbiting the sun. Without gravity, our world would be a very different place. So next time you see something fall, remember gravity. It's the force that keeps us grounded, literally. A long time ago, people thought heavier objects fell faster than lighter ones. This belief was so widespread that it was considered common sense for centuries. Makes sense, right? A bowling ball seems like it would plummet faster than a feather. After all, the bowling ball is much heavier and seems like it should cut through the air more quickly. But guess what? They were wrong. This misconception was challenged and eventually overturned by scientific inquiry. A brilliant scientist named Galileo Galilei proved them wrong. Galileo was a pioneer in the field of physics and astronomy, and he had a knack for questioning established beliefs. He did an experiment, maybe even dropping things from the Leaning Tower of Pisa, though historians debate that. The story goes that he dropped two spheres of different masses and observed that they hit the ground at the same time. He showed that without air resistance, objects fall at the same rate, regardless of their mass. This was a groundbreaking revelation that changed the way we understand motion. This means a feather and a bowling ball would fall at the same speed in a vacuum. Imagine that. Two objects that seem so different behaving in exactly the same way when air resistance is removed. That's because gravity pulls on all objects with the same acceleration, which we call g. This universal force acts equally on all masses. On Earth, g is about 9.8 meters per second squared. This means that in the absence of air resistance, all objects accelerate towards the ground at this constant rate. Galileo's discovery revolutionized our understanding of gravity and motion. It laid the groundwork for future scientists like Isaac Newton to develop even more comprehensive theories. It showed that the universe operates by laws we can discover and understand. Pretty cool, huh? This realization opened the door to countless scientific advancements and continues to inspire curiosity and exploration today. One-dimensional motion is like riding a gravity train that only goes up and down. Imagine throwing a ball straight up. It goes up, slows down, stops for a brief moment, and then comes back down, getting faster as it goes. Gravity is the conductor of this train, constantly pulling the ball downwards. As the ball goes up, gravity slows it down. As it comes down, gravity speeds it up. We can describe this up and down motion using some fancy words like displacement, velocity, and acceleration. Displacement is how far the ball traveled from its starting point. Velocity is its speed and direction, and acceleration is how quickly its velocity changes. Understanding one-dimensional motion is key to unlocking the secrets of freefall. It's the foundation for understanding how objects move under the influence of gravity. Now let's add a dash of math to the mix. Math isn't just about numbers and symbols. It's a powerful tool that helps us understand the world around us. Don't worry, it's not scary. In fact, math can be quite fascinating and even fun when you see how it applies to real-life situations. We have special equations to describe the motion of objects in freefall. These equations are not just random, they are derived from fundamental principles of physics. These equations relate displacement, velocity, time, and acceleration due to gravity. By understanding these relationships, we can predict and analyze the motion of falling objects with great accuracy. One equation is dE equals VOT plus 1/2 at squared, where dE is displacement, V is initial velocity, T is time, and A is acceleration, which is G for freefall. This equation helps us determine how far an object will travel over a period of time. This equation tells us how far an object falls in a given time, but it's amazing to think that with just a few variables we can predict the distance an object will cover as it falls. Another equation is V equals VD plus at, where V is final velocity. This equation is crucial for understanding how the speed of a falling object changes over time. This one lets us calculate the velocity of a falling object at a specific time. By knowing the initial velocity and the time elapsed, we can find out how fast the object is moving at any given moment. These equations are like magic formulas that unlock the secrets of free fall. They allow us to delve into the mysteries of motion and understand the forces at play. With them, we can calculate how long it takes for an object to hit the ground, how fast it's going when it does, and much more. These calculations are not just theoretical, they have practical applications in fields like engineering, aviation, and even space exploration. So next time you see something fall, remember the math behind it and let it make you go, whoa! Section 5, Solving Freefall Mysteries, Detective Work for Science. Solving freefall problems is like being a detective. You're given clues, the knowns in the problem, and you have to use your knowledge of freefall and the handy-dandy equations to find the missing pieces, the unknowns. First, read the problem carefully. What do you know? What do you need to find out? Then choose the right equation to connect the knowns and unknowns. Don't forget about units. Make sure you're using consistent units throughout your calculations. Otherwise, your answer might be way off. With a little practice, you'll be solving freefall mysteries like a pro. It's all about breaking down the problem, using the right tools, and thinking logically. Section 6, Projectile Motion. It's not just falling, it's flying. Projectile motion is like free fall, but with a twist. It's what happens when you throw a ball at an angle and it follows a curved path. Think baseballs, basketballs, or even that crumpled up paper ball you aim for the trash can. Projectile motion has two components, horizontal and vertical. The horizontal motion is constant, meaning the object travels at the same speed in a straight line. The vertical motion is affected by gravity, so the object goes up, slows down, stops, and then comes down, just like in free fall. We can still use our trusty free fall equations to analyze projectile motion. We just need to separate the horizontal and vertical components and treat them as two separate one-dimensional motions. Section 7, Real-World Wonders. From baseballs to satellites, projectile motion is everywhere. A baseball soaring through the air, a basketball swishing through the net, a fountain spraying water in an arc. These are all examples of projectile motion in action. Even rockets launching into space utilize the principles of projectile motion. They are launched at an angle to achieve both altitude, vertical motion, and distance, horizontal motion. Understanding projectile motion helps us design everything from better sports equipment to safer cars. By understanding how objects move through the air, we can make them fly farther, higher, and with greater accuracy. Section 8, Space, the final frontier for freefall fun. You might be thinking, what about space? Is it really the ultimate playground for freefall? There's no gravity up there, right? Well, that's a common misconception. Actually, gravity is everywhere in space, but it behaves differently than it does on Earth. Gravity is a force that exists throughout the universe, and it gets weaker the farther you move away from massive objects like planets and stars. Objects in space, like satellites and the International Space Station, are actually in a constant state of free fall. This might sound surprising, but it's true. They're constantly falling towards Earth, but they're moving so fast horizontally that they keep missing the planet and stay in orbit. This delicate balance is what keeps them afloat. It's like throwing a ball so fast that it curves around the Earth and keeps going. Imagine the speed and precision required for such a feat. That's essentially what satellites do, just on a much larger scale. They orbit our planet, providing us with vital services like communication, weather forecasting, and GPS. So even in the vastness of space, the principles of free fall and projectile motion are at play, keeping our universe in motion. These principles govern the movement of celestial bodies and man-made objects alike. It's pretty amazing, right? The dance of gravity and motion is what makes space exploration possible and keeps our universe in harmony.